The binomial distribution. Binomial distribution requirements and example. A binomial experiment is a probability experiment that satisfies the four following requirements. There must be a fixed number of trials. Each trial can have only two outcomes or outcomes that can be reduced to two outcomes. These outcomes can be considered as either success or failure. The outcomes of each trial must be independent of one another. The probability of a success must remain consistent from trial to trial. We will let n represent the number of trials. P will represent the numerical probability of a success. Q will represent the numerical probability of a failure, which is also the complement of P. X will represent the number of successes. The formula for the probability of exactly X successes in n trials is the probability of X equals to n factorial divided by n minus x factorial times x factorial multiplied by p raised to the x power times q raised to the n minus x power. According to the Bureau of Labor Statistics, 23% of the U.S. workforce in 2015 was employed in the wholesale and retail trade industry. If 8 U.S. workers are randomly selected, what is the probability that exactly 3 are employed in the wholesale and retail trade industry? Let's check and make sure that all of the criteria for the binomial experiment are satisfied. There must be a fixed number of trials, which is n equals 8. 8 workers will be randomly selected, so n will in fact be 8. Each trial can now only have two outcomes, or outcomes that can be reduced to two outcomes. These outcomes can be considered as success or failure. There are only two possible outcomes. Either the selected worker is employed in the wholesale and trade industry or not. So we will assign a success as the event that a selected worker is employed in the wholesale and retail trade industry. The outcomes of each trial must be independent of one another. The employment industry of one randomly selected employee is not influenced by the industry of employment of another, so the outcomes of each trial would be independent of one another. The probability of a success must remain consistent from trial to trial. The Bureau of Labor Statistics reports that 23% of the U.S. workforce in 2015 was employed in the wholesale and retail industry. So the probability of success will remain constant at 0.23, and the probability of a failure will remain constant at 0.77, which is 1 minus 0.23. Since we have determined that the criteria for a binomial experiment are satisfied, we can use the formula for calculating a binomial probability to find this probability. So we will substitute 8 for n, 3 for x, and 0.23 for p, with 0.77 for q. So the probability that exactly 3 out of the 8 randomly selected U.S. workers in 2015 would be employed in the wholesale and retail trade industry would be 0.1844. Calculating a binomial distribution using a graphing utility. According to the 2012 Pet Ownership and Demographics Sourcebook, 36.5% of U.S. households own at least one dog. If 10 U.S. households are randomly selected, what is the probability that exactly 4 would own at least one dog? Let's make sure that all of the criteria for a binomial experiment are met. There are a fixed number of trials. 10 households will be randomly selected, so n is equal to 10. There are only two possible outcomes. Either a household owns a dog or does not. we will assign a success to finding a household that owns at least one dog. The outcome of each trial must be independent of one another. Whether a randomly selected household owns a dog has no effect on the probability that another household also owns a dog. The probability of success remains constant 0.365 from trial to trial. We are asked to find the probability that out of 10 randomly selected households, exactly 4 would own at least one dog. In probability notation, this can be expressed as the probability that x is equal to 4. We should use the binomial PDF function on your graphing calculator to find a binomial probability associated with one value of the random variable. In order to use the graphing calculator to calculate binomial probabilities associated with a single value of the random variable, we will use the binomial PDF function. So we will begin by clicking second vars, and then we will cursor down until we get to the binomial PDF function. Click Enter. In this example, the number of trials is 10. The probability of a success is 0.365. We are to find the probability that there would be exactly 4 successes. Click Enter, and then paste. If you are using a graphing calculator that does not present a menu for entering the required values, then you will need to place the values in order. That will be n first, then p, then x, with commas in between each value. Press Enter. And now we find that the probability is 0.2444, rounded to the nearest 4 decimals. Let's take a look at this example once again, but with a slight twist to it. Notice the difference between what is being asked this time compared to the last time. In particular, I refer to the phrase, at most. According to the 2012 Pet Ownership and Demographic Sourcebook, 36.5% of U.S. households owns at least one dog. If 10 U.S. households are randomly selected, what is the probability that at most 4 would own at least one dog? The probability that at most 4 would own at least one dog can be written in probability notation as the probability that x would be less than or equal to 4. Since this is a discrete random variable, we can find this probability by adding together the probability of 0 successes, the probability of 1 success, the probability of 2 successes, and the probability of 3 successes, along with the probability of 4 successes. Fortunately, it is not necessary to calculate each of these probabilities individually. We can use the binomial CDF function on your graphing calculator to find a binomial probability associated with several values of the random variable, namely the values from 0 up to a given value. In order to use your graphing calculator to find an accumulation of binomial probabilities, we will use the binomial CDF function. We will do that by pressing second, and then press the vars button, and then cursor down until we find the binomial CDF function, then press Enter. In this example, the number of trials was 10. The probability of success was 0.365. We were asked to find the probability that x would be at least 4, and then cursor down to highlight, paste, then Enter. If you are using a graphing calculator that does not present a menu for entering the required values, then you will need to place the values in order. That order will be n, then p, then x, with commas in between each value. Press Enter. And we find that this probability is 0.7177 if we round to 4 decimal places. Let's take yet another look at this same example, but with yet another twist. In particular, I refer to the phrase now, at least. Notice the difference between this time and last time. According to the 2012 Pet Ownership and Demographics Sourcebook, 36.5% of U.S. households own at least one dog. If 10 U.S. households are randomly selected, what is the probability that at least 4 households would own at least one dog? The probability that at least 4 would own at least one dog can be written in probability notation as the probability that x would be greater than or equal to 4. Since this is a discrete random variable, we can find this probability by subtracting the probability that x would be less than or equal to 3 from 1. We can do this by using the binomial CDF function from your graphing calculator. In order to use the graphing calculator to find a probability that is greater than or equal to some value, we must subtract an accumulated binomial probability from 1. So we will begin by typing 1 minus, then press second, vars, then cursor down until we find the binomial CDF function. Press enter. The number of trials is 10. The probability of success is 0.365. This time we're going to find the probability that x is greater than or equal to 4. So we will have to subtract the probability that x is less than or equal to 3 from 1. Cursor down and highlight paste, then press enter. If you are using a graphing calculator that does not present a menu for entering the required values, then you will need to place the values in order. That order will be n, then p, then x. With commas in between each value, press enter. And we will find that this probability is 0.5267 if we round to 4 decimal places. Let's go ahead and follow along with our student notes. Some variables can have only 2 outcomes, or the outcomes can be classified in exactly 2 categories. For example, when a coin is tossed, it will land on heads or tails. In addition, a multiple choice question with 5 options will have 1 correct choice and the other 4 choices will be incorrect. Thus, the answer choices can be classified as correct or incorrect. This is still considered a binomial experiment. Each repetition of the experiment is called a trial. A binomial experiment is a probability experiment that satisfies the following 4 requirements. 1. There must be a fixed number of trials. 2. Each trial can have only 2 outcomes or outcomes that can be reduced to 2 categories. These outcomes can be considered either success or failure. 3. The outcomes of each trial must be independent of one another. 4. The probability of a success must remain the same for each trial. Successes and failures. A success in a binomial experiment is neither good nor bad. A success just means that the result was what the researcher was looking for. For example, a multiple choice test is given and the outcomes are either correct or incorrect, given the binomial nature. If the researcher is looking for the probability of incorrect answers, then an incorrect answer would be considered a success. On the other hand, if the researcher were looking for the probability of correct answers, then a correct answer would be considered a success. Let's go ahead and classify each of the situations as binomial or not. First, rolling a standard die 200 times, standard being 6-sided. This clearly would not be binomial. It's not binomial because each trial has 6 different outcomes, not 2. B. Survey 100 shoppers asking for their favorite exercise shoe brand. This is also not binomial. And that's because there are so many different exercise shoe brands, more than just 2, certainly. 3. Survey 100 teenagers and ask them if they play the video game Halo. This is definitely binomial. The answer is either yes or no. Next, ask 300 viewers if they recall seeing a Coca-Cola commercial during a particular show. Well, once again, this is either yes or no. And since there is yes or no as the outcomes, 2 outcomes, it's binomial. And finally, test 4 brands of aspirin to see which brands are effective. This is clearly not binomial. There are 4 brands, each with their own individual outcomes. The outcomes of a binomial experiment and the corresponding probabilities of these outcomes are called a binomial distribution. Here is some notation that we use for binomial experiments. N will equal to the number of trials. X will equal to the number of successes in N trials. P of S will equal to the probability of success. P of F will equal to the probability of failure. P will be the numerical probability of success, that is, P of S equals to P. Q will be the numerical probability of failure, that is, P of F equals 1 minus P, that is Q. Note that P is the complement to Q. In a binomial experiment, the probability of exactly X successes in N trials is as follows. It looks rather complicated at first, but after a few tries, it's really not that hard. In fact, you can also use this in your calculator and allow the calculator to do the simplification for you. Recall, this first factor is simply just the formula for combinations. This calculation can also be computed using technology. Keep in mind that no successes, x equals 0, must also be considered. Let's do an example. A 6-sided die is tossed 5 times. Now you might think if it's 6-sided, it cannot be binomial. However, the researcher decides that a success is whether or not you toss a 2. A failure is tossing anything other than a 2. Therefore, that has created a binomial experiment. Each toss of the die is independent of any other toss. Now there is a 1 in 6 chance of tossing a 2, whereas there is a 5 in 6 chance of not tossing a 2. Let's go ahead and find the probability of getting exactly 3 2s. In other words, let's find the probability of rolling 2 3 times. Then we'll find the probability of getting at least 3 2s. Next, the probability of getting at most 2 2s. Before we get into it, though, it would be wise to create a table of probabilities. Do this every time you perform a binomial experiment. First, the probability that we do not roll a 2 at all. Now recall, we are rolling the die 5 times. Plugging into the formula, you'll notice we have 5 factorial in the top, which relates to the rolls. And the bottom, it's 5 minus 0 factorial times 0 factorial multiplied by the probability of success raised to the 0 power times the probability of failure raised to the 5 minus 0 power. Pause the video here, simplify this yourself, and see if you get the same result as I do. And you should get 0.4019. What's the probability after 5 rolls that we roll a 2 once? Here, you can see, I simply replaced the 0 with a 1. The 5 continues to remain where it is. Here I got the same answer. And by the way, that's just coincidental. That's not always how it happens. Now the probability of rolling a 2 twice out of 5 rolls. Simply replace the 1 now with a 2. Now the probability of getting 3 2s out of 5 rolls. You'll notice that the probabilities are going down. The probability of getting 4 2s in 5 rolls. And finally, what's the probability that I roll 5 2s in a row? To reiterate, this first probability was the probability that we roll no 2s at all in 5 rolls. Then the probability that we roll a 2 once, the probability that we roll a 2 twice, and so on. Let's do the first one. Let's find the probability that we get exactly 3 successes. That is, 3 2s out of 5 rolls. We notice a very familiar sight. As you can see from the previous table, it's right here, being that the probability of rolling 2 3 times out of 5. Now, what if we look for the probability of at least 3 successes? In other words, what's the probability that x is greater than or equal to 3? The phrase at least means greater than or equal to. Well, that would include the probability of getting 3 plus the probability of getting 4 2s plus the probability of getting 5 2s. So by simply adding up the probabilities from those respective rows, we get 0.0355. What about the probability that we get at most 2 successes? This refers to the inequality of less than or equal to. So here we get the probability that we get no 2s plus the probability that we get 1 2 plus the probability that we get 2 2s. Adding those up, 0.9645. Let's do another example. In a survey, 3 of 4 students said that the courts show too much concern for criminals. Find the probability that at most 3 out of 7 randomly selected students will agree with this statement. First, we'll note our probability. P in this case will be 3/4, or 0.75. We deduce this from the fact that 3 out of 4 students said the courts show too much concern. So the probability that at most 3 out of 7 agree with this statement, recall, at most means less than or equal to, would give us the probability that no one agrees, plus the probability that 1 agrees, plus the probability that 2 agree, plus the probability that 3 agree. Here, we'll need to evaluate each one of these probabilities individually. So once again, we're looking for the probability that at most 3 out of the 7 agree. The probability that none of the 7 students agree is calculated as follows. 7 factorial divided by 7 minus 0 factorial times 0 factorial times the probability P of 3/4 to the 0 power times the complement of 1/4. Remember, you just simply subtract from 1 to the 7 minus 0 power. Then we add that to the probability that 1 of the 7 agree with the statement. Notice here I'm simply replacing 0 with 1, but everything else remains the same. Now we go ahead and add that to the probability that 2 out of the 7 agree with the statement. And finally adding that to the probability that 3 agree with the statement out of the 7. Once again, this looks slightly complicated. However, with the aid of a calculator and a little bit of practice, you should be able to get the same numbers as me. Pause the video here, evaluate this expression, and see if you get the same decimal value as I do. The answer I got is 0.0705566. Now let's take a look at a binomial probability table. If 20% of children were reported to want a particular toy, use the table to find the probability that exactly 4 out of the 7 children want that toy, at most 3 of the 7 children want that toy, and at least 4 of the 7 children want that toy. It is very important to note the difference between the words exact, at most, and at least. We'll start with exact. First, let's find the section of the table for n equals 7 children and the column for 20%, rather 0.2. If we zoom in on this portion of the table, where we have 7 children, and we go ahead and take a look at the column for 20%, you'll see a 0.2 or a 20% up top. Follow it down. We'll end up in this column here. So the probability that exactly 4 of the 7 children want that toy, you'll go down to 4, and you'll see we get 0.029. And so, P of 4 in this case would equal to 0.029. Let's find the probability that at most 3 of the 7 children want that toy. Again, go to the rows for n equals 7, but this time take a look at x equals 0, 1, 2, and 3. And then we'll add those 4 probabilities. The probabilities I refer to are these first 4 here. Adding those 4 up, we get 0.967. Now let's find the probability that at least 4 of the 7 children want that toy. Again, look at the rows for n equals 7 children. This time we'll look at x equals 4, 5, 6, and 7. And then add those probabilities. I refer to these 4 rows here. Notice we have no values here and here. That's because when the values are smaller than 0.001 for this table, no value is printed. So in other words, we simply go ahead and add 0.029, 0.004, and 0.000 plus 0.000, giving us 0.033. The mean, variance, and standard deviation for a binomial variable can be found using the methods for any probability distribution, but there are shorter, mathematically equivalent formulas for the mean, variance, and standard deviation for the binomial distribution. So whenever you have a binomial distribution, you are welcome to use the previously learned formulas. However, in this section, if you can recognize you have a binomial distribution, use the following simpler equivalent formulas. First, with the mean. The mean mu is simply going to be n times p. In other words, the number of trials times the probability of success. Next, the variance will simply be n times p times 1 minus p. In other words, the number of trials times the probability of success times the probability of a failure. And finally, standard deviation will simply just be the square root of the previous slide. These formulas are especially helpful when, for a binomial experiment, the number of trials is very large. Let's do another example. For a binomial distribution for which there are 500 trials and the probability of success is 0.25, what is the mean, variance, and standard deviation? Well, quite simply, for the mean, you simply just multiply 500 times 0.25, and we get 125. The variance, once again, is n times p times 1 minus p. That is 500 times 0.25 times 0.75, giving us 93.75. Simply take the square root of the variance, and we get the standard deviation. Another example. 32% of adult internet users have purchased products or services online. For a random sample of 200 adult internet users, find the mean and standard deviation for the number who have purchased goods or services online. Now, is this a binomial experiment with 200 trials and a probability of success of 0.32? The answer is yes. Whereas the two options or the two possible outcomes are those who have and who have not purchased goods online. There are a fixed number of trials, 200, and each trial has two possible outcomes: has purchased online or has not purchased online. Each trial is independent. The probability of success remains the same for each trial. The mean number of adult internet users out of 200 who have purchased products or services online is simply 200 times 0.32, which gives us 64. The standard deviation of adult internet users out of 200 who have purchased projects or services online is 6.59697. In a survey, 3 of 4 students said that they purchased products or services online. Find the mean and standard deviation for the number of students who say they have purchased products or services online out of 7 randomly selected students. The mean, quite simply, will be 7n times 3/4, which is p, giving us 5.25. Standard deviation, number of trials, times p, times q, all inside of a square root, 1.1456. And finally, in a survey, 20% of children were reported to want a particular toy. Of 7 children, what is the mean and standard deviation of the number of children who want the toy? The mean, 7 times 0.2, 1.4. The standard deviation, 7 times 0.2 times 0.8, 1.05.